Hi, I'm Antoine Yang and I'm gonna present you NAS evaluation is frustratingly hard, a work we've done at Huawei Noisar Club. A little bit of background to start. The architecture search is a field that aims at automatically designing the best architecture for a given task. It can be decomposed into three main components: a search space, a search strategy, and a training protocol. Our main contributions address critical issues in the evaluation of search strategies. Nowadays, most NAS methods fail to compare against an adequate baseline. So we'll propose a benchmark of 8 NAS methods on failed datasets using a simple random sampling baseline. Additionally, it's unclear how each component really contributes to the final test accuracy. So we'll propose a study of each of these components. For the benchmark, we selected 8 reasonably fast NAS methods. The random sampling baseline consists in randomly sampling an architecture from the method search space, then, without searching, training it with the method's training protocol. This ensures that when we compare this baseline to the corresponding method, only the search strategy is evaluated because the search space and the training protocol are shared between this baseline and the corresponding method. We found out that all NAS methods we considered on all datasets considered consistently fail to significantly outperform this trivial baseline. To evaluate the importance of the training protocol, we randomly sampled 8 architectures from the well-known DAT search space, and we trained them with diverse protocols on Cypher10. We observed that there are significant differences between the different protocols in terms of test accuracies. Additionally, our best architecture with the best training protocol achieved 98.15% test accuracy, which is only 0.25% below state of the art. This is very close, given how big is the search space, and given that we only randomly sampled 8 architectures. We also proposed a study of the well-known DAT search space. To know more about the random sampling distribution, we randomly sampled more than 200 architectures from this search space that we trained on Cypher10 with DAT training protocol. We observed that the test accuracy distribution is very narrow and that its mean is very high. We had very similar distribution when replacing all convolutions in the search space with inefficient vanilla convolutions. This suggests that it's likely the macrostructure, the cell structure, that makes these networks work so well on average, rather than the microstructure, the operations, which is what we are searching for in NAS. Because all these architectures perform all similarly, we wondered, does changing the training seed really change the results? So we randomly sampled 32 architectures that we trained with 2 different seeds, and we observed that the architecture's ranking heavily changes as measured by the Kendall autocorrelation. We also measured the importance of the depth gap. In NAS, we often search using a small network of 8 cells, and then in the end, we stack a larger network of 20 cells. But what we saw is that there are significant differences. There is a significant change in the architecture's ranking when we just change the number of cells, as measured by the Kendall autocorrelation. Finally, we suggest some best practices for future works in NAS. When comparing search strategies with baseline, the NAS method should either report the results with the same training protocol and same search space than previous methods, either update the results of the previous works with their new search space and their new training protocol. We also believe that random sampling provides a very simple, search-free, yet very powerful baseline to evaluate a search strategy. In terms of generability, evaluating on a various set of datasets could avoid overfitting and could potentially highlight too costly hyperparameter tuning. In terms of search space design, if the goal of AutoML NAS is to find the optimal architecture without any human intervention, then it would make much more sense to consider a wider search space where we could actually evaluate whether the method is able to discard the bad solutions. Thanks.